Today we're going to be talking about how to find the general solution of a second-order differential equation. And in this particular problem, we've been given the equation y double prime, or the second derivative of y, plus 4 times y prime, or the first derivative of y, plus 4y is equal to 0. Now for this particular second-order differential equation, we know that it's a homogeneous second-order differential equation because on the right-hand side here, we have this function equal to 0. Now it's a non-homogeneous differential equation if the right-hand side is some function in terms of x. Ours happens to be homogeneous because it's equal to 0. Now, when we're solving a homogeneous second-order differential equation, the first thing we want to do is take the left-hand side here and find the roots of this equation, or the solutions to this equation. The way that we're going to do that is by factoring the left-hand side. But first, we need to change our y variables, y prime, and y double prime, into variables in terms of r. So a little easy, silly trick I like to use is I like to count the hash marks on each y variable here. That tells me what my exponent is going to be when I convert this to r variables. So for example, this y double prime here, there are 2 hash marks on the y variable. That means that my new r variable is going to be r squared. So I'll replace y double prime with r squared. Here for the second term, y prime, I have 1 hash mark, so that's going to give me r to the first power, or just r. So I get plus 4r. For the third term here, y, I have no hash marks, right? There's none here. So that's going to give me r to the 0. Anything raised to the 0 power is just 1, so I'm going to get 1 there. 4 times 1 is just 4, so all I'm left with here is 4. That's how I like to change the equation from y variables into r variables. So that's what I get for the left-hand side. We're going to leave the right-hand side equal to 0. Now that you've simplified the equation, your next task is going to be to factor the left-hand side. In our case, the factoring is pretty easy. We just get r plus 2 times r plus 2 on the left-hand side, and we set that equal to 0. Now here we need to set each factor individually equal to 0 on the right-hand side and solve for r. So if we set the first factor, r plus 2, equal to 0, we get r equals -2. Now, if we set the second factor equal to 0 here, we get r plus 2 equals 0. We get r equals -2 again. Now, in this situation, our roots are equal to one another. We got 2 roots. Both of them are equal to -2. In this situation, we have what's called equal real roots. Our roots are real numbers and they're equal to one another. Because we have equal real roots, that means that we're going to be using the formula that I've written up here. Now, keep in mind that you can have 3 types of roots. You can have equal real roots, which is what we just got here. You can have distinct real roots where both of your roots are real numbers, but they're different from one another. They're distinct from one another. So if we'd gotten -2 and 4, that would be distinct real roots, and that would be a different equation than the one I've written up here. Or the third option, you can have complex conjugate roots where you have roots involving the imaginary number I. Now, I have videos about how to deal with distinct real roots and complex conjugate roots. In this particular video, we're just going to talk about equal real roots. So when we have equal real roots, we plug them into this formula here. Our roots are r sub 1, right? We just found one of them, so they're both equal to r sub 1. We're going to be plugging them in here for r sub 1 and r sub 1. The rest of the variables in this equation will go ahead and leave as they are. So our general solution and our final answer is y of x equals c sub 1 e to the -2x plus c sub 2 x e to the -2x. And this is our final answer, even though we haven't solved for c sub 1 and c sub 2. If you're given initial conditions to go along with your equation, you can use those initial conditions to solve for c sub 1 and c sub 2 and get a particular solution instead of just a general solution. But in this case, since we don't have those initial conditions, we're just looking for the general solution, y of x, and we've got it here just by plugging our equal real roots into the formula that we have here.